Hey folks, it's time to talk about molecule polarity. We've talked about bond polarity, but what about the whole molecule? Remember, polarity means we have a positive side and a negative side. So we're talking about a positive side to a molecule and a negative side to a molecule. Molecule polarity requires two things. You have to have polar bonds so that the electrons are being unevenly distributed on a bond situation, and you have to have an overall pull of electrons to one side of the molecule. Let me show you what I mean. If I have the molecule F2, this diatomic molecule, the difference in electronegativity is 0, which means that there is no pull on the electrons one way or the other. The electron density is going to be pretty evenly distributed across this molecule, and so that leaves this guy being nonpolar. Next up, I have carbon dioxide. So if I look at my molecule, and this is my structure and it is linear, if I look at each bond, again, you have to go bond by bond for bond polarity. Oxygen is more electronegative than carbon, and these are polar covalent bonds. And so you end up with dipole moments that are directed towards the oxygens. But if you look at it, they're going in exactly opposite directions, and they're the same size because you've got the same difference in electronegativity. It's like playing tug of war. If you've got two kids of equal strength, the flag's not going anywhere. Even though this has polar bonds, it is a non-polar molecule. And that is because there is no net pull on the electrons in the molecule. They're still going to be evenly distributed because they're being pulled in two different directions that are exactly opposite of one another. My third example, HCN. The HC bond is nonpolar, and so I'm not going to draw a dipole moment arrow for that one, but the carbon-nitrogen bond is. And the dipole moment points towards the nitrogen. If you look at this, I have a polar bond, but I also have a net pull. There's nothing counteracting the pull on electrons towards that nitrogen. And so this molecule will have polar bonds and be a polar molecule. In order to be polar, you both have to have polar bonds and you have to have a net pull on those electrons. If you're going to look at a formula and determine whether it represents a polar molecule or a nonpolar molecule, there's some steps you have to follow. You have to start by drawing a Lewis structure. You need to figure out how many bonds you have, how many lone pairs you have, all that kind of stuff. Determine your electronic and molecular geometry because it will dictate where the electron density is in your molecule. Draw the molecule with the proper geometry. Don't skip this step. Lewis structures are misleading. They're two-dimensional. Molecules are three-dimensional, so draw them out. Then you're going to determine bond polarity and then draw the dipole moment arrows that exist. And lastly, look at it to determine if there's a net overall pull on your electron density. Let's look at two similar examples and we'll do a bunch more in class. Okay, carbon tetrachloride. I'm going to nab it and get myself a Lewis structure. This molecule is tetrahedral in both electronic and molecular geometry. And so when I go to draw it, I want to make sure I draw it looking tetrahedral. So I will do that next. Okay, I have my molecule. Remember, a tetrahedral shape is extremely symmetrical. So now what I'm going to do is I'm going to draw my dipole moment arrows. These are polar covalent bonds, and they're going to pull in all directions. Now, last step, is there a net overall pull? No. In a shape that is symmetrical, those pulls will cancel. Even though I have polar bonds, this is a non-polar molecule because the symmetry means that all of the poles will cancel out in all directions. So if you have symmetry in a truly symmetrical shape, you're going to end up with a non-polar molecule, even if you have polar bonds. The other one, on the other hand, let's fast forward through a nabbed Lewis structure and get ourselves to a drawn shape with the proper geometry. Okay, here we are. Time to look for polar bonds. Carbon-hydrogen bonds are nonpolar. I'm not going to draw any dipole moment arrows on those bonds, but that carbon-chlorine bond, that one is polar. And now as I look at the whole molecule, it's no longer symmetrical. The dipole moments are no longer symmetrical. And so as a result, this one is a polar molecule. Now you might be asking me yourself, or sitting there thinking to the screen going, I could have told that from the Lewis structures. Let me give you one last example to emphasize why you must draw the molecule in its proper shape. The last molecule I'm going to include here is water. It is potentially the most important molecule because it's so much of the world around us. So we have to do our nabbing, we have to draw the Lewis structure, all that kind of good stuff. And now as we look at it, we're going to take the time to write this with the proper shape. This is a tetrahedral electronic geometry and a bent molecular geometry. Okay, now that I have the molecule in its shape, now I can look for polar bonds. Yes, the oxygen-hydrogen bond is polar, and the electron density is being pulled towards the oxygen for both of those bonds. Is that pull going to cancel in all directions? No, it's not. But you would have thought it did had you left it as a Lewis structure, because though we draw our Lewis structures, the hydrogens are opposite one another. But in 3 dimensions, they're not. You have to take the time to do this. This is a polar molecule. Oh, and I can say that the overall, what we call the net dipole moment, is going to point upward towards the oxygen. So in this case, upward as I have it drawn, because those dipole moment errors are both going up and in. The in parts are going to cancel out, but the up parts are actually going to add. And so you have a net dipole moment in the direction of the oxygen for this molecule.